Okay, welcome everyone to the Thursday afternoon session of the CFPU 2026 AI Winter School. Today's session will be led by Jeff Schuler from the University of New Mexico, who will be telling us about object detection for rare event searches, in particular for the Migdal effect. Um, as a reminder, if you have any questions, put them in the Q&A and we'll try to deal with them as they come in. And you should have access to the shared Google Drive um, through the link in the Google group. Please put it in the Q&A if you cannot get to the Google Drive. And with that, I will um, suggest invite Jeff to share his slides full screen, and then we'll go on from there.
Fantastic. Thank you very much for the introduction, Jan. Okay, fantastic. So, yeah, as Jan said, my name is Jeff Schuler, and I'm a postdoc at the University of New Mexico. And so, for this afternoon's module, I'm going to be talking about a computer vision technique that's called object detection and how it can be applied to rare event searches. And specifically, one of the themes I'm going to be focusing on is how, for certain classes of rare event searches, it enables you to train on real data, which is something that is really useful. So let me just start by giving a quick overview of the session and how it's going to be laid out. So I'll start by giving you an introduction to the Migdal effect in the Migdal experiment, because that's the specific rare event search that we're focusing on today. Then we'll go into the Google Colab module. So I'm splitting that up into two parts. So the first part is going to be going through a non-machine learning based Migdal effect search. So this gives you just kind of an idea of how you can search for the Migdal effect in a traditional way, and it'll give you build your intuition on what the Migdal effect looks like and how to find it. Um, then in step three here, that's when we're going to jump into the machine learning aspects. So I'll introduce object detection and how we can apply it for real data training for our rare event search. Then for the second part of the module, that's going to be where you'll apply an object detection pipeline to search for the Migdal effect, and you can compare that performance to how we do with our traditional baseline search. Then if there's time at the end, I'll talk about some extensions. So one is called segmentation, which you can use to separate overlapping particle tracks. So in general, you can separate overlapping objects and image data using this technique. And so we'll talk about how we use that in the Migdal experiment. And then finally, I'll just briefly highlight some other rare event searches where object detection could be of use. Um, so I guess, are there any questions before we get started? Okay, we'll just hop right into it. So I'll start by introducing the Migdal effect and the Migdal experiment, and then we'll get into the first part of the module. So whenever I talk about the Migdal effect, because there's actually a couple different kinds of Migdal effects, the one that we're interested in is the Migdal effect in nuclear scattering. And so what this is it's the low probability atomic excitation that's induced by neutral particle scattering. But what does that actually mean? So let's look at this figure in the middle right here. And the idea is you have a neutral particle. So it could be a theoretical dark matter particle, it could be a neutron, it could be a neutrino. And when it scatters off of an atomic nucleus, that nucleus recoils. Um, but when you think of the entire atomic system, what ends up happening is that recoiling nucleus is you can think of it as a sudden perturbation. And so your electron cloud actually lags a bit behind. And in the time that it takes for the electron cloud to catch up to the recoiling nucleus, there's a small transition probability that an electron can be emitted. And this electron emission that's induced by the recoiling nucleus, that's something that you can detect. So that's what the Migdal effect is. Why do we care about this? Well, it's actually really relevant for light dark matter searches. And when I say light dark matter, I mean light WIMP scale dark matter. And so it turns out that the Migdal effect has allowed existing direct dark matter search experiments to lower their mass sensitivity. So it's allowed them to extend their mass sensitivity to sub-GeV dark matter masses. And so I'm not going to go into the full details there, but the general idea is the direct dark matter detection searches, what the way that they search for dark matter is by measuring nuclear recoils. So they measure this recoiling nucleus and the ionization signature that it makes in their detector. Um, but it turns out that when if your dark matter mass gets sufficiently low, then the energy of the recoil that's induced by your dark matter scattering gets too low for detectors to detect it. It's below their detection threshold. But it turns out that the electron emission via the Migdal effect can actually be above their threshold. So it effectively allows these detectors to lower their detection threshold, and that allows them to set these limits. So all that you really need to take away from this is these uh, very sensitive dark matter limits, all of these experiments with red arrows next to them evoke the Migdal effect to set their exclusion limits. But why we care about measuring the Migdal effect is even though a bunch of experiments have used it to set competitive low mass dark matter limits, the Migdal effect's never actually been measured. So they're using theory to rely on this, but we want to be able to measure this so we can actually confirm Migdal effect cross section so we can validate these limits. So that's the physical motivation on why we're interested in measuring the Migdal effect. Now let me talk about our experiment. So our experiment is a neutron scattering experiment where we have a high intensity source of neutrons. It comes from a deuterium-deuterium generator. This produces a beam of 2.5 MeV neutrons that we have incident on our detector through a collimator. So we have a collimated neutron beam that's going into our detector. Our detector is called the gas time projection chamber. And so for those who aren't familiar with how these work, I'll go through just roughly on this slide. So inside this black box is our actual detector setup. We fill our detector volume with low pressure 50 torr CF4 gas. The way that we make a measurement in a TPC is neutrons enter your detector and the neutrons can scatter off of the gas nucleus in your volume. So a neutron can scatter off of a carbon or a fluorine, and that produces a nuclear recoil track, which is shown right here. And in the rare event that the Migdal effect actually occurs, we also get that simultaneous electron emission. And so that creates this two-pronged track where you have what we call a nuclear recoil and an electron recoil sharing a vertex. So this is the signal that we're interested in detecting. The way that we actually detect it is not, we don't detect this primary ionization that's created here. What we do is we drift this against an electric field. So in this picture, it drifts downward. And then we amplify this signal using a micropattern gas detector. So these are glass gas electron multipliers that amplifies this signal by about a factor of 100,000. And then we image that signal with two complementary readouts. So the first one, which is shown on the left here, we call this our ITO anode. What it is it's basically just a segmented strip readout where we have 120 strips that are segmented along the x-axis, and they record, each strip records ionization charge versus time. And this ultimately gives you a picture that looks something like this in its XZ projections of your event. What we also image is we use an optical camera with a lens that images scintillation light that's produced in this event. So CF4 is a scintillating gas. So after the ionization is amplified in your GEMS, we measure the scintillation light and it produces an image that looks something like this. It gives you XY projections of your event. And so what we're going to be focusing on in the module today is exclusively data from the camera readout. So we're going to be looking at images, a lot of images that look like this. And so ultimately, the goal of the Migdal experiment is to directly image and characterize the Migdal effect for the first time. Okay, so let's get into just again what the Migdal effect should look like in our detector. So this is an image that we recorded. And for reasons that I'll get into later, this actually isn't the Migdal effect, but it looks a lot like it. And so it's a good illustrative picture just to guide your intuition on what this event should look like. And so the idea, if this were the Migdal effect, is your neutron comes into your detector, it scatters, creating this very bright track, which is a nuclear recoil. Um, and and also it ejects the electron recoil, which is this very faint head that's poking out right here. So something to pay attention to is the intensity scale. It's a logarithmic intensity scale. So this nuclear recoil, the bright broad track, is orders of magnitude more intense than the electron recoil track. So what we're looking for is a nuclear recoil or a bright nuclear recoil and a faint electron recoil that overlap with each other. Um, so just to say a bit about our camera image data, just to give you a little bit of context. So we record images at 120 frames per second, which is about an 8 millisecond exposure, which for the purpose of finding, the instantaneous emission of an electron relative to a nuclear scattering event, that's actually pretty slow. And so what ultimately ends up happening is we sometimes record multiple tracks per frame, which you can see here. There's 5 tracks here, and this really highlights before doing image processing just how dim these electron recoil tracks are compared to your nuclear recoils. Um, and but I guess for the purposes of today, what I really want to focus on are just the data rates. So we're recording 120 frames per second of roughly 2 megapixel images. So that's to about 2 terabytes of image data per hour. And so obviously that's way too much data to be able to handle in a Google Colab session. So for our purposes today, to alleviate these data burdens and also some of the image processing steps that are needed to be able to identify these tracks nicely, we're using simulation. And in particular, we're using simulation that doesn't have any camera readout noise. And this is because it allows us to store track data in sparse coordinates, which what that means, if you've never heard the term sparse coordinates, it just means any pixel hit that fires above 0, it only stores that. So you can see if you thought of only your signal as non-zero pixels here, the vast majority of this camera frame is empty. So we're not storing those empty coordinates. And this allows us to store thousands of tracks that you can analyze the physics of in less than a gigabyte of data. So the last thing that I'll say before we do part 1 of the module is that sample Migdal effect event looked nice, and you could see both the nuclear and electronic recoil component of it. In practice, challenging the Migdal, measuring the Migdal effect is often very challenging. So not only is the Migdal effect incredibly rare, we expect to see it in about 1 in every 100,000 nuclear recoils that we detect. But even when we do see it, the signal is hard to detect. So yeah, go ahead, Jan.
There's just a question for clarification. The Migdal effect is the idea that dark matter causes the big Migdal by striking a nucleus, and then the nucleus itself will generate. So you get an electron scattering that it's associated with the output.
Yeah, exactly. So it's basically um, as the nucleus recoils and the electron cloud catches up to that recoiling nucleus, you can actually compute this using the sudden approximation in quantum mechanics. There's a really small transition probability that an electron's going to be ejected. And so that creates that electron recoil signal in your detector, which is what this little guy sticking out of the big nuclear recoil is. And so that's why the events that we're looking for look something like this, a nuclear recoil and an electron recoil sharing a vertex. Another thing to add to this is the electron recoil, fortunately, does the direction, the ionization profile of electron recoils just so happens that the brightest part of the electron recoil is at the end of the track, which really helps us. But you can imagine if the electron recoil is emitted parallel to the nuclear recoil direction, you're going to be out of luck. It's going to be completely buried under an orders of magnitude brighter nuclear recoil. But anywhere that kind of goes out along where my mouse cursor is, in principle, is detectable. Um, Okay, which this actually this ties in nicely to this plot here. So what this plot is showing is it's showing the theoretical Migdal emission rate. So you can think of this as the Migdal interaction probability. That's the color scale, jointly as a function of the emitted electron energy and the nuclear recoil energy. And again, notice that the color scale is logarithmic here. So what this means is higher probabilities are in red, lower probabilities are in blue. So as your Migdal, as the emitted electron via the Migdal effect, as its energy decreases, your chances of observing the Migdal effect, or rather the chances of the Migdal effect arising, increase exponentially. And so what that means is these deep red regions with high nuclear recoil energy and low electron recoil energy, that's the region where the Migdal effect is most likely to arise. And here's an example of what an event might look like in this regime. So you have a very high energy nuclear recoil right here. And if you stare really closely at this, you might be able to convince yourself that there's an electron recoil poking out here. But the point is, not only are we only seeing the Migdal effect or expecting to see it in 1 in every 100,000 nuclear recoils, but when it does arise, oftentimes it's going to be very difficult to detect. So this gives some context into our search. And the connecting it back to this cross-section plot to the left here, the lower your electron recoil energy is, the shorter your electron recoil track is. So it just doesn't have that much space to poke out. So that makes our search pretty challenging. Okay, so let's go ahead and open up the Colab module now. So we're going to start by quantifying Migdal effect detection without using machine learning. Let's see, we'll use the one that I just opened. Okay. So I hope that everybody has this open. I'll actually take a sip of water and give people time to open up the module.
And if we should be able to access it through the Google Drives through the shared drive link, you should have access to the Brown CFPU 2026 notebook, and it should be labeled which folder. Um, as a reminder, you don't have write access to the drive, so you should make you right if you right click on the actual module on the actual notebook, you should have the option to make a copy, and you can make yourself a local copy of it. If you have any issues, post it in the Q&A.
Yeah, that sounds good. So I'm going to get started slowly, but please stop me if folks are having trouble. So we'll walk through this step by step. What I'm going to start with is this line right here. So the intention is to run this module on a GPU, particularly for part 2 of this module. So just to get us set up for that, if you haven't already done this in your previous modules, let's click on runtime up here and then change runtime type. And currently mine is set to the CPU. If you don't have Colab Pro, I think T4 GPU is your only option, and that's more than enough for our purposes today. So click T4 GPU and save. And I will note, if you run out of your GPU usage limits, that's okay. You don't have to run this module on a GPU, and the GPU running step, that data output we've saved, so you can open that without having to spend 45 minutes running a cell today. Okay, so I'm going to just start with going through the first modules here. So when you run your notebook. If this warning pops up, just click run anyway. Um, and then the second cell right here is if you have GPU access, well, rather, if you have a CUDA capable GPU, so an NVIDIA device, this will return true. And again, if it returns false for you, that's not an issue, but true is confirmation that running with the GPU worked. Um, okay, so we'll mount our Google Drive as you've done in the previous modules. I'll press continue and continue. And as I understand, some of you might have to do multi-factor authentication, so we'll wait a moment for that. Okay, so um, this cell that I'm running right now, cell number 4 that has the utility function for the Unix tree command, this is kind of the crucial step that I want to make sure that this works for all of the participants. So provided that you have access to this directory that's highlighted, then it should run okay for you. And assuming it does, if it then the cell won't error out, and you should get an output that looks like this. And the one thing that I would just like one participant to confirm to Jan before I move forward is that this highlighted part, sorry, that says test new with images and labels, that this shows up on the user end. Because if it doesn't, then we're going to have to change a couple things. So let's hope that this does work for the users.
If anyone has gotten to this step, please put in the Q&A a got here message.
Yep. And again, confirming that this test new folder shows up, that the highlighted one.
Okay, so it worked for one person, which means at least
Okay.
from the point of view of access to the drive, it should not be a problem for anyone.
Yep. That's confirmed for me as well. This means that we don't have to extract the tarball, which is good. So, okay. So then just to walk you through the data structure here. So this, of course, is the module that you're running right now, and this just shows the directories and subdirectory structure of the module, if you've never seen this command before. So what we're going to be working primarily with is this pandas data frame. So we'll be opening this up later, and this has the data for all of the tracks that we're going to be analyzing. And then when we get to the object detection part, we're using an algorithm that's called YOLO, and it has some images of particle tracks that it's going to be analyzing. So that's going to be in part 2. Okay, so this next cell, we do need to run it. You can ignore most of the text here. It just puts some more data paths into memory to make sure that we can call them as we move further along into the module. And this is just printing the same tree as before. Okay, so since everyone can presumably access the test new folder here, let's look at a couple of the images that are here. So we're defining basically the path to this test new images folder. And then we're using Python's OS module to list the first 5 files in that path. And so you can just see it is numbered PNG images. So what do some of these look like? That comes here. So this large cell. Okay, so when you run this cell, you should see something that looks like this, where you see 6 event images. I'm assuming that they'll be the same as the ones that are showing up here, as well as a color bar next to them. And so this is just to give you a feel of the raw images that we have in our simulation set. So what you'll notice looking at these is, in general, there's more than one track per image. And again, like I showed in the example in the slides, the high intensity events here, so the bright colored ones that are nearer to red, these are nuclear recoils. And you'll also see that there's some faint blue events that are orders of magnitude fainter. Those are electron recoils. And if you look at some of these images, like this track where my mouse cursor is right here, this is a Migdal effect event, or at least it looks like one. You have a nuclear recoil and then a faint electron recoil that's poking outward. So again, just as a reminder, in real data, we expect this to only arise in 1 in every 100,000 nuclear recoils or so. But in the simulation set, we have a lot more Migdal effect signal baked into it, so you can quantify how well your algorithms do at identifying the Migdal effect. Okay, so this brings us into our baseline search that doesn't use machine learning. So the first step is we'll load in and look at I'm calling it our metadata. Really what this is it is the true simulated information about each particle track that's here. So one other thing that I want to mention that's important is this, this data frame has all of the track information for every track in all of these frames, and it's organized in such a way that it's already, you can think of it as it's already identified each individual track. So it'll have a separate entry for this track compared to this track. That's actually a non-trivial step in your analysis when you're dealing with images with multiple tracks. You would need to apply some sort of clustering algorithm. And the machine learning algorithm that we do, you will start with just these raw images and do the entire search from that. But for the purposes of this non-machine learning search, let's pretend that we've already done that perfectly. So we know that this track is a nuclear recoil. We know that this track that my mouse cursor is pointing to is a Migdal. And we'll see that when we look in this data frame. So we have 4,702 rows. This corresponds to 4,702 individual tracks. And whenever I'm looking at data for the first time, when I use pandas, I like to use the dot columns command because this basically tells you exactly what's in your data frame. So there's a bunch of columns in this data frame. And so what I've done is told you which ones are relevant for today. And so we're actually going to filter this data frame and only keep the columns that are of interest for today. And we'll go through these columns in a moment. The first column that I want to bring your attention to is truth class. So what this is since we simulated these events, we know what the events are. We know whether they are an electron recoil, which is ER, a Migdal, or a nuclear recoil, NR. So for each row here, there should be a truth class associated with it, and you can see there is. This, of course, in a real analysis, we wouldn't have this because we wouldn't know a priori what the tracks are. Okay, so now let's look at an electron recoil, a nuclear recoil, and a Migdal. And this is just looking at the structure of our data here. So you can see the output of this cell, it says ER sample event, then there's NR sample event, and Migdal sample event. This is just kind of the exploratory phase of looking at our data. What you can see is the frame number column. You'll notice it's frame number 16 for the electron recoil. Same with the nuclear recoil and the Migdal. So this is just telling you that there can be multiple tracks in the same frame, which is exactly what we saw when we plotted these pictures up here. But again, the tracks have been separated out. Now, the other things that we have in here is we have the length of the track in millimeters. We have the track's energy. This is in keV. And this energy actually is a quantity that's given to us by our simulation. And so we call this a truth energy. It's the true energy of the event at the generator level. This is something that you wouldn't have in real data. So the next cell below actually, it computes the intensity of the track, which the intensity of the track is just the sum of all of the pixel values in the track. So that's your intensity. And in a real detector, what you would do is you would calibrate that pixel intensity scale using some sort of radioactive source where the tracks that it produces are of a known energy. And so you can do that, and then you calibrate the energy scale of your detector. So I'm going to reprint out this right here that shows the electron recoil, nuclear recoil, and Migdal. And you can see now the intensity column's been added here. We'll say more about that shortly. The other things to note are the X min, X max, Y min, and Y max. These ERBB, the BB stands for bounding box. That's relevant for part two. But this just gives you the minimum and maximum X and Y coordinates of the electron recoil. Notice that since this is just an electron recoil event, the nuclear recoil part is all set to -1. So basically when I guess maybe this will make more sense if you look at the Migdal event. Since the Migdal track is a composite of an electron recoil and a nuclear recoil, it has the individual constituent parts. It has those track boundaries. So the minimum and maximum of the electron recoil and of the nuclear recoil component. Whereas the isolated nuclear recoils just have unphysical written for the electron recoil component. Okay, so that's just a cursory walkthrough of the contents of our data frame. Actually, the last part, apologies. This part's important. You'll notice that there's these quantities that are stored as arrays instead of as numbers. What these are the pixel hits. So these are the pixel hits that are above 0. And so this is the X and Y, the 337.79 is the X and Y coordinate of the first pixel in this track. And the value of its pixel intensity, which I'm calling a charge here, is 2. And so if we use this information, we can view these tracks individually. And so that's what's done when you look at the cell that says simple track viewer. Whenever you have a data frame that looks something like this, you can image your tracks by making a histogram of them. So I've run it, and you can see this shows an image of your track. The way that this code block works, if you've never seen something like this before, is we make a 2D histogram of our pixel hit data. So we have the X and Y coordinates of our pixels, and then rather than just counting the number of hits in a given bin, yeah, question?
Just a very simple question. Are the pixel coordinates defined based on the center of the pixel or the corner?
I think here it's the corner. But yeah, it depends on how you set your bin boundaries here. And so in our case, I'll get to that part in just a second. So we're looking at basically binning the X and Y coordinates and then weighting it by the charge. Because if we didn't have this weight, it would just tell you the number of times an X and Y coordinate had a hit, but we want it to actually be the sum charge of that hit. So that's why we weight it by this QCAM. And then this gets into how we bin our events. So the actual images that we record are 2048 by 1152. For this simulation, to keep the data burn smaller, I've downsampled this by a factor of 4 in both the X and Y dimension. So these are 512 by 288 pixels. And so that's what's shown in this bins in range category here. And then to get this to just render correctly, you transpose this histogram. So this gives you an image, and you can view whatever events you want here. So you can view, well, the first thing is you can put this on a log scale by changing the log parameter to true. And you'll immediately notice with the log scale set to true, so this is a Migdal event, you can see the electron recoil portion a lot better than when it's on a linear scale. And yeah, you can view whatever events you want to look at here. This one's just a plain nuclear recoil. This one's a Migdal. Here's a Migdal that has a much higher energy electron. This is kind of a nice one to see because you can see the electron sticks really far out. And yeah, that's what I'll say. Well, one other thing that you can do is if you want to just look at Migdals, you can do queries in your data frame. So you can say that the truth class is equal to a Migdal, and this will give you the 243rd Migdal event or the 0th Migdal event. If you want to look at an electron recoil, you can change this to ER. You can see these are much fainter. So that's the simple event viewer. You can do the same sort of thing and build up a more complicated event viewer. And so that's what this code block does here. And what this does is it just shows you the truth track that you have here. So this, what's plotted here, actually, we did the query. This is the 1000th nuclear recoil in our data frame, and it shows it next to its raw PNG image. And you can see this box is given by the boundary of your track. So that's that NR bounding box, Y min, Y max, X min, X max. And so there's several options that you can view. So this next cell is an electron recoil. We have some Migdals. And in general, on your own time, you can play around with these. The one thing to note here is, again, the Migdal, even though it's listed as one track in this data frame, it is a composite. It's a composite of a nuclear recoil, which is the bright track, and the faint electron recoil. And you can see that with the boxes that are drawn around here on the truth data frame. So the red box is the nuclear recoil, the white box is the electron recoil. Okay, so now that we know how to view these events, let's discuss how we could do a Migdal search for these events. So again, this is assuming we have the tracks like this on the left-hand side. And so just to build a little bit of intuition, and in a sense, when you just look at the events here in the columns that we have here, it definitely gives you a big hint here. Notice that we have the length of the track written out and the track's summed intensity. These are sort of the standard way that you would do a Migdal effect search. Rather, track intensity and track length, these are standard quantities that are used to select between different particle species in gas time projection chambers like our detector. And just to build up your intuition on why this could work for a Migdal search is you can look at this track right here. You'll notice the nuclear recoil portion. Let's pretend that there's no electron recoil and just look at the nuclear recoil. It's going to have a very high energy because it's in the high intensity scale here. And the addition of the electron recoil component doesn't add much to its energy. These are orders of magnitude lower energy than the nuclear recoil. So it only adds a tiny amount of intensity to the nuclear recoil, but it adds a noticeable amount of length to your track. And so what that tells you is that using this energy, I'm going to use energy and intensity interchangeably, but using intensity and track length is a discriminant that you could use to select for the Migdal effect. So that's what we're going to try to do here. So these next two cells are going to plot intensity versus length of all of the events that we have. So again, this is just a pandas way that we're doing this to is what we're doing is we're grouping our data frame by the truth class. So by whether it's an electron recoil, a nuclear recoil, or a Migdal. And then we're aggregating the intensity and lengths together so we can plot this in this next cell. So once you plot this, you have intensity versus length, and you see you have your electron recoils, which you can barely see. They're down here. Your nuclear recoils and your Migdal events in green. So the first thing that I want us to do is, so essentially what we're going to do is we're going to try and come up with selections based off of intensity and length that give us good performance at identifying a pure sample of Migdals. So that's our signal without background nuclear recoils and electron recoils. And so looking at this plot right here, you can immediately see that we should be able to reject the electron recoils outright. So this is a simple exercise to start with. In this next cell, there's this cut string right here. Determine a cut on intensity that is going to get rid of all of the electron recoils while keeping all of your Migdals and nuclear recoils. So I'll give everyone a minute just to fill that in for themselves. This is the wrong answer. So when you plot this, it shows that there's 100% of nuclear recoils kept, but also 100% of electron recoils kept. We want the nuclear recoils kept to be 100% and electron recoils kept to be 0%. And for this plot, I've baked the Migdals and nuclear recoils together.
Again, if there are any issues with accessing the drive or the notebook and making a copy, put questions in the Q&A.
Hmm. And you can also post answers in the Q&A for this one. Do I just click Q&A to be able to view those, Jan?
Yep, that's right.
Okay.
You should get a little window that says Q&A.
So we have answered. Those are, I see.
Yeah,
Yeah,
they'll
so
show up they'll show up as open questions.
perfect. So just fill in your answer as an open question. So just what intensity does this have to be? There's not a unique right answer. There's multiple right answers, but pick an intensity that rejects all of the electron recoils, but keeps all of the nuclear recoils in Migdals. And I'll stop sharing for just a second. Oh, now I don't know how to check. Oh, there it is. Okay, I see one answer.
One answer so far.
Yep, I'll wait for a couple more. And if anything's unclear, please also ask that, or please ask a question.
On the error putting in a low answer, I suspect that the answer has to be in EV.
Uh, I guess here it's arbitrary units for the intensity. But I think what might happen, let me just reproduce that error right now. It doesn't show an error for me, but it gives a warning that basically nothing passes that cut. Okay. So let me share the screen again. So the first answer that was given was what was it, 0.5 e to the 6, so 500,000. And I mean, just looking at this right now, so that for folks who don't understand this cut string part, I guess this is something that is relevant. What this cell is doing is it's saying that the nuclear recoils, which are the events that we're keeping, so this is the filtered data frame, it is taking all events in our original data frame and only keeping those where the intensity is greater than 0.5 times 10 to the 6, which here we have our scale is up to 10 to the 7. So that might have been something else that confused people. Looking at the Python vertical axis, this is 1 times 10 to the 7th, not 1. So I apologize if that was something that was missed. But noting this, if you put 0.5 times 10 to the 6, that's somewhere where my mouse cursor is. That looks pretty good. So that's going to be within this gap. And so if you only keep events above that, then let's check. Yeah, we've kept 100% of our nuclear recoils and rejected all electron recoils. So that was a nice simple cut to make. So we're going to keep this cut moving forward. So this is our nuclear recoil cut. It's an intensity of 500,000. Okay, I think someone else put, okay, perfect. Alrighty. So now let's talk about how we can actually, so now we've gotten to a point where we have Migdals and nuclear recoils. And so we want to filter between these, and you can see there is a region where you have Migdals that are separated from nuclear recoils. And this is exactly the intuition that I was showing you on the track earlier. These tracks for kind of a given energy or intensity. So for a constant value along your y-axis, you have longer tracks because those electron recoils are sticking out. They're not adding appreciable energy, but they are adding appreciable length to your track. So now these next steps are going to look at quantifying our ability to separate out Migdals from nuclear recoils. And so the quantities that we use to do this are called efficiency and purity. So this text here just goes through, if you're familiar with machine learning, you've probably heard of precision and recall. And if you have a particle physics background, you might be familiar with signal purity and signal efficiency. What I'll say off the bat is precision is mathematically equivalent to signal purity, while recall is mathematically equivalent to efficiency. So what we're plotting is the same as a precision versus recall curve, which is relevant for people who have a machine learning background. But we're looking at it in terms of the particle physics language of signal efficiency versus signal purity. So this is the definition of both of these quantities. Let's look at an example of this. So if we plot this next cell, what you should be seeing is, okay, I should have changed this to intensity versus length, but it's the same idea. So energy versus length here. You see a diagonal line right here. And this is what I'm calling our cut boundary, this diagonal black line. And I'm saying, let's only keep events that are to the right of this black line. If you only keep events that are to the right of this black line, you just have this one green dot right here. And so what this is you have a tiny efficiency, and that's because efficiency is whenever you make a cut, it is the number of total signal kept in your sample divided by, the number of total signal kept after you make a cut divided by your number of total signal. So here you've kept only one signal event out of all of your signal events. So you have a tiny efficiency. This is rounded. But then the other quantity is purity, which is of the events after you've made your cut, what fraction of those are signal? How pure is your sample? And here it's entirely pure. You don't have any backgrounds that are contaminating this. So what this plot cut function does is it just says, okay, I've kind of arbitrarily drawn a line with this slope, and you can shift this in an arbitrary direction. So you're just shifting the intercept, you're keeping the slope the same, and you're looking at the purity and efficiency. So if we shift this 6 units to the left, which is defined in the function, um, this is where your black line is now. And if you were to look at the events to the right of this black line, you see that they're mostly green. So you're keeping mostly your Migdal signal events, but you are contaminated with some orange. And so when you do this, your efficiency is increased by quite a bit from 0.001 because you're keeping a lot more of your original signal after your cut, but your purity decreased. It went down to 0.88, and this is because you're now being contaminated by some backgrounds. So this is something that you can play around with on your own. If you shift it even further, now your efficiency is really high, but your purity is awful. You have a lot of, you're keeping 97% of your Migdal events, but only 25% of the events that pass this cut that are to the right of this line are actually Migdals. You're contaminated by nuclear recoils. So the way that that cuts-based analyses like this quantify their performance, one way to do it is to, instead of just shifting by arbitrary numbers like this and plotting your efficiency and purity, instead you can just sweep through small shifts in your vertical intercept here, and then plot the purity and efficiency for the at each step. So that's what this code block does here. It just generates a list of purities and efficiencies based off of where this line is. And then you can make a plot that looks like this. So what we're plotting now is purity versus efficiency at different values of where that black line is to derive this cut. And you can see that using, so I've plotted two things. I've done one where we were using these 2D cuts, which is what we're plotting here with energy and length. You can also use a cut in one dimension where you're only cutting based off of the length of your tracks and you're not accounting for the energy. And what you end up finding is, I guess the first thing to note is perfect performance. If you were perfect at being able to select the Migdal effect, it would be in the upper right-hand corner of this plot. You'd have an efficiency of 1, meaning you keep all Migdal events with your initial cut, and a purity of 1, meaning there's no background contaminating it. And clearly with our energy versus length cuts, we don't do so well. We do okay, and we do better than what you do with length only cuts. But we would like to move this further to the upper right-hand corner of the plot, which is what we're going to do shortly with machine learning. So just to contextualize this plot, that's what's shown in the text down here. So this sample that you're looking at is an idealized sample that has a way higher ratio of signal to background than what we have in our real experiment. Remember, in our real experiment, for every 100,000 of these orange points, we expect to see 1 green point. And so that means that you're going to be flooded with a bunch of nuclear recoils and very few Migdals. So in this real plot, your purity would be much lower than what's shown here. And with a rare event search like ours, what you really want is, I mean, you want both purity and efficiency, but you need to make sure that your purity is essentially 100% here, because you need to be able to pick out that 1 in 100,000 Migdal events. But the problem with using a method like this energy and length cut or intensity and length cuts is where by the time we reach 100% purity, we're only at like 15 to 20% efficiency. That means that we would need to run our experiment 5 times longer to achieve the same performance that we would get if we had an optimal classifier, an optimal identifier. I see that there's a question here. Let's see. Is there a reason why the cuts are linear? Just for the purpose of illustration. That's actually a really good point. If you were trying to come up with a truly optimized cut here, you would want something that kind of matches the curve of the boundary between the nuclear recoil background and your Migdal effect signal. So this was just to illustrate the buildup of this purity to efficiency plot. Um, and so now I think I've said everything that I want to say here. So let's see. Yeah. So basically the point is you could run using an analysis like this, but you'd have to run your experiment a lot longer to have a chance to be able to unambiguously detect the Migdal effect. And that takes a lot of time and resources in order to be able to do that. So if we can come up with an algorithm that gives us much better purity and efficiency, that's what we want, because then it reduces the amount of time we need to run for a chance of discovery. So that's the idea behind all of this. Um, okay, so I will move back to the slides. And so now we can start on the machine learning part. So let's introduce object detection. And also, you might be wondering, how could we possibly train a machine learning algorithm on real data for a rare event search when we're expecting to see so few of these events? Um, okay, so I think I already gave you a pretty good overview of this earlier, but just to really hammer this in, we're expecting 1 Migdal per 100,000 events. We're recording about 2 TB of raw image data per hour, or 3 million frames that we have to analyze per 8-hour shift. So we have a ton of data, an extremely rare event search, and the signal can often be difficult to elucidate. So it makes sense that we want to use machine learning for our search. And so the first thing that we tried was doing supervised classification, which I'm pretty sure you all saw this, at least in your introductory module, where you say, okay, let's use a convolutional neural network and train it to identify the Migdal effect in your input image. So if you have a well-trained neural network, it'll tell you that this is indeed the Migdal effect, and it'll give you a confidence score if you softmax your output. Um, so that was the first thing that we tried. What we ended up doing was we trained a ResNet, which was the state of the art, I would say, in image classification in the mid 2010s, but it still performs well in general. So we trained a ResNet on simulation to distinguish between our Migdal effect signal and several classes of background events. And this is the purity versus efficiency curve that we got for that when we evaluated it on test set simulation. So it looked really promising. I mean, we really want to prioritize that 100% purity regime, but we're seeing something like, if you're looking at optimizing the product of purity and efficiency, which is often a good way to uh, optimize your performance, you can see we're looking at something like 95% efficiency with 98% purity. So this looked great. Then we tried this on real data, and we got, when I say a bunch of false positives, I mean like every other nuclear recoil that we looked at, it said was the Migdal effect. Um, so what happened? I mean, the first thing is this didn't work on real data. And if you have experience, especially doing machine learning and particle physics, deep learning models that you train exclusively on detector simulation, they tend to generalize really poorly to real data. This is called a sim to real gap. And the reason why is when you're using a deep learning algorithm like a convolutional neural network, it's basically learning information at pixel level granularity. And so unless your simulations are representative of real data at a pixel level of granularity, which ideally they should be, but in practice it's pretty difficult to do that. It's going to struggle without some finagling. So there's really 2 potential ways to proceed. You could either train on real data or improve simulations. Ideally, you want to do both. The approach that we took is to train on real data. And so this brings us back to that question, but this is a rare event search. How can we possibly train on real data? And so now let me introduce object detection, which is the machine learning technique that we use. So This slide goes over some common computer vision tasks. I think you've probably seen some of these between the modules that you've attended so far. Um, but the idea for each of these 5 examples that are shown here is your input data is image data, and your output is going to vary based on the task at hand. So you've already seen classification, which is just you train a model to given an input image to predict a discrete set of outputs. So this could be used for particle ID, including looking for the Migdal effect. But again, training on simulation that didn't work for us. Regression's the same idea where you input an image and your well-trained model will output a continuous set of variables instead of a discrete set. So you could use that for energy reconstruction, for instance. There's several other quantities that you could regress, of course. Object detection is our application of interest, and it's a combination of classification and regression. And what object detection algorithms do is given an input image with any number of objects of interest, the algorithm is trained to simultaneously classify and localize each of those objects. So in this image, it does that by drawing bounding boxes. And I've colored the bounding boxes to show the class predictions that are given. And so in this case, red is a nuclear recoil, pink is an electron recoil. So the rest of today is more or less devoted to object detection. There's some other extensions of object detection. And this list that's shown on this slide is not exhaustive. There's quite a bit more. But you can take object detection a step further and do something called key point detection, where for each object that's detected, you can train an algorithm to identify a discrete set of key points within that object. So in particle physics, you could use this, for instance, for trajectory fitting, for tracking decay vertices, for tracking the directions of tracks, so where the head and the tail of the track is. And then there's also various forms of segmentation. What's shown here is instance segmentation, where for each object, so each bounding box that's defined, the pixels within that bounding box are masked. The pixels that are relevant to that track are shown. So I'll note that this is a very rich field. There's so much that we're not going to talk about today. But segmentation really shines in physics. There's been some great examples of it being done in 3D analyses, and the neutrino community has done some fantastic work here with liquid argon TPCs. So there's a link to a GitHub page here. And at the end of today, if there's time, I'll discuss how the Migdal experiment uses segmentation. But so the rest of this module is going to highlight our use of object detection. You'll be focusing on our simulated Migdal data set, and we'll talk about how we use it on real data in the slides. Okay, so with that said, now that you have a sense of what object detection is, how do we train on real data for a rare event search? The idea is actually really simple. So the fact that the Migdal effect is a composite signal, it consists of the overlapping electron recoil and nuclear recoil, we can use that to our advantage because in our detector, we measure a ton of electron recoils and nuclear recoils in isolation. So what we can do then is we train an object detection algorithm to get really good at identifying electron recoils and nuclear recoils in isolation. We also have some instances where they overlap. Since we're using an optical camera, we can increase the exposure time, and that gives you more of these coincidences where you have overlapping tracks that aren't actually the Migdal effect, but they look like the Migdal effect. And so the idea is you train an algorithm on enough of these electron recoils and nuclear recoils that once it's trained and you give it, in this case, a Migdal effect, this is a simulated Migdal effect event, it'll give you what you want. It gives you a bounding box around the nuclear recoil part and the electron recoil part. And I'll say that this actually is what our trained algorithm gave us on this track. So it was able to find that tiny electron recoil that's poking out. So the point here is once your algorithm is well trained, you're not training your algorithm to explicitly detect the Migdal effect. What you're training it to do is to detect the overlapping nuclear recoil and electron recoil. And then you can use the proximity of the contents within the bounding boxes that your algorithm finds. So the contents within the nuclear recoil and electron recoil to select for the Migdal effect. So that's what we do. Um, so the actual algorithm that we use in our experiment is YOLO, which stands for You Only Look Once. This is a link to the original paper, which is over 10 years old now. But the YOLO family of models is very popular for object detection in a bunch of different fields. So not just particle physics, there's medical applications, there's agriculture, there's self-driving cars, you name it. Object detection is a very versatile field. But recently, Ultralytics, they've released several new iterations of the YOLO model. We're using version 8, which when we started using it was among the current state of the art for fast object detection, but this is a rapidly progressing field. So now I think YOLO 11 or maybe YOLO 12 is the most recent release by Ultralytics. But a couple notes. So what you want to, if you're developing an object detection pipeline for your own application, you really do want to think about which model is best for your use case. So we wanted to use YOLO because it's known for being fast, and that allows us to actually perform our search in real-time speeds. So we're able to actually run through our images and analyze them faster than the 120 frame per second acquisition rate of our camera. Um, so we can do our entire search analysis essentially in real time. And furthermore, you can do it without really expensive hardware. You don't need data center level things in order to do this. We do it on a consumer desktop PC with like a $1,500 GPU. But now let's get into this note here. So there's plenty of alternatives for YOLO depending on your use case. I would say if you want the most accurate object detection, and again, it's really hard to know a priori what's going to work best, but I would say the state of the art now are vision transformer based models. So here's just a couple that are listed. The Detter family of models. This RF Detter is new and does really well on the standard computer vision benchmarks. But there's also legacy CNNs. So there's the RCNN families. There's a feature pyramid networks, so on and so forth. There's also foundation models that are multimodal image to text models that you can give text inputs. And like if there's an image of a cat, you'll tell it to draw a box or to find the cat and it'll automatically be able to draw a bounding box around the cat. So there's a lot of things that object detection is used for. You could, in particle physics, you could maybe imagine coming up with a foundation model where you're using data from two different readouts and you're developing a model that learns to combine those readouts and perform object detection on them. There's a lot of stuff that hasn't been done yet and can be done. But anyway, with that digression aside, let's just give you a small glance at YOLO version 8. So I'm not going to go into detail about the architecture because it's a relatively complicated network. This link does show the full diagram of the architecture. Let's see, I guess there's time to say a little bit about this. So essentially, what we're doing is supervised learning, meaning we have to train with labeled data sets. Actually, yeah, I am going to skip this, but we'll go back to it later on if there's time. So for now, that was just to tell you the inner workings of YOLO version 8, which it is complicated, but when all is said and done, and you break down all of the pieces and you train your model, you can get something that works nicely for our use case of searching for the Migdal effect. I think what's more important is on the application side, how do you train YOLO? So today, even on the simulation that we have, we're not going to do any training. So we're going to be inputting a pre-trained model. But the way that we trained YOLO using real data is you have to have bounding boxes on the tracks that you have because bounding boxes are your output. So as well as classification scores associated with those bounding boxes. Um, so we label our data by hand, um, which is pretty time consuming, but it's not anything that is completely unfeasible. And so in if you're working on an application where you need to hand label your data, there's a lot of free and open source options for labeling. So I'm highlighting Label Studio here because that is the software that we use in Migdal to label our events. But there's other alternatives that are available. The one thing that I do want to note is the reason why I'm emphasizing free and open source options is you can imagine computer vision is a big field, not only in academia, but also in industry. And so there's a lot of enterprise level labeling softwares that require kind of enterprise level, they have an enterprise level price point. And the point that I want to hammer in is we were able to easily train YOLO for our purposes for free and using this Label Studio software. And we've also built our own software. It's not our own labeling software, but our own software that's associated with our pipeline, where we have some plugins that we wrote for Label Studio that allow. So let me take a step back for a second. One of the nice things about Label Studio is it's very customizable. And so you can actually load in pre-trained models into the Label Studio backend so that when you flip through your images that you load into the software, it automatically draws bounding boxes for you. So that's what's actually shown here. This is something that these bounding boxes were drawn by the software with a pre-trained YOLO model that I fed Label Studio. So then rather than having to click and drag, you start with these bounding box templates and you just edit them as needed and you can generate a bunch of labels. So when all was said and done, we ended up labeling about 10,000 images, the vast majority of them being electron recoils and nuclear recoils because those are the constituents that make up the Migdal effect. And so when we did our training, it doesn't take that long for the 10,000 images that we labeled. It took a couple hours to fully train YOLO on a consumer desktop PC. Okay, so thank you for bearing with me on all of that. So now let's apply our pipeline. And so the hope is, even though we're doing this on data that's specific to Migdal, you'll be able to adapt some of these tools as needed for your own use cases. So I'll just continue on in the notebook that I have. So go ahead and navigate to part 2, which is the YOLO-based search. And the first cell that we're going to run is installing the Ultralytics package. So Ultralytics has been the developer of the modern versions of YOLO for probably the last 5 years or so. There are other versions of YOLO that are not developed by Ultralytics, but I like using the Ultralytics package because the software is very user-friendly and plug and play. So it doesn't take that much work to set up an object detection pipeline for yourself that uses YOLO. So once you've run this first cell that installs Ultralytics, then this second cell just checks sort of your computing configuration. So here I still have the CUDA capable Tesla T4 that has, 16 gigabytes of memory, or I guess 15 gigabytes. Okay, so the first thing that we want to do is, so we have our truth data frame. Remember that this is indexed by track. What I want to do is I want to re-index this data frame so that it is indexed by raw frame. And this is because I want to transform this data frame so it looks like the data that we actually measure in Migdal. So what this group by statement does is it just groups all events by frame number, and then it aggregates the information from each track in a given frame. And so, yeah, question.
Yeah, there's a question about whether how well YOLO does with this task of training on simulations and then segmenting real images. Has anyone
Uh,
tried that?
and then, so training on simulation and then applying it to real data. Um, so I have not tried that. I've done some studies where I augment real data trained sets with simulation, and depending on how you make that simulation, which I'll say a bit more on that in the slideshows, because so much of this depends on how well your simulation actually models the real physics of your detector. If you do it with high enough quality simulation, it does help, is what I found for Migdal. Um, but our baseline was just trying on real data because then we don't have to worry about fine tuning our simulation to get it to match well with real data. Okay, so um, now we've done the group by statement. This is just to show you the contents of the data frame, which I know this is a little dry, but essentially what we've done is now this first frame, which is frame number 16, we've aggregated all of the tracks together. So we've aggregated, there's an electron recoil, a Migdal event, and a nuclear recoil in this data frame. And so we've aggregated all of the summary quantities into lists. So here's the length of the electron recoil, length of the Migdal, length of the nuclear recoil. And the reason why I'm doing this is so the data that we're analyzing looks the same as our real event images. So what this event viewer does is it looks at this group data frame, it concatenates all of the vector data together. So it concatenates the pixel level data for each of the tracks in your frame, and then it plots them as a 2D histogram. So that's what's shown here. And just as a sanity check, so this is coming from our data frame, let's make sure that this looks the same as the raw PNG image from that YOLO folder. And sure enough, it does. So this is, whenever I'm doing transformations like this, I always like to visualize events, and I always like to do sanity checks. I think it's a good idea just to make sure that you're doing everything correctly. Um, okay, so now that we have a way to generate a physical image that corresponds to these PNG images that we're going to pass through YOLO, we can develop our analysis pipeline. So I'm going to go through this step by step, and we're going to do it one event at a time. If you've never used Ultralytics, which I'm expecting most of you have not, some of it's going to look a little bit opaque. So I would definitely recommend going through some of this on your own time if you're interested. So the first thing that we're going to do is, so we have our model path. So this was just from looking at, here, we'll add in just to be transparent. So we'll do os.list dir data path. So basically in our data path, we have all of these folders here. I forget what the view tree command was that we had, but needless to say, we have in our data folder that corresponds to this module, there's a YOLO weights folder. And then if you look at inside the YOLO weights folder, there's going to be this file. What this is it is a PyTorch neural network weights file. So it is the weights of our trained YOLO model. So we pre-trained a YOLO model before this to work with this simulation. So going back to the question that was asked a few minutes ago, this pre-trained model is not the real data trained model. This is a model that is trained on this simulation. So it's apples to apples with the simulation that we're using. In a sense, it's going to be idealized performance. But okay, so once you have your data paths handled properly, you can load your model. And we also want to look at the images that we're going to be passing through our model. So there's 1986 PNG images that we're going to pass through our YOLO model, and it's going to predict bounding boxes on the tracks in those images. So let's run YOLO on a single test image. So we're using PNG images. That's what we're feeding into YOLO. So all we need to do is define the file path to the PNG image. So we're just using this first image in the list of images that we have. We're opening it with the PIL library. And then to get results, you just take your model, which we defined in the previous cell, and we do model.predict. We're predicting for that single image. This is your batch size. So if you want to operate this faster, you can, load in batches of images at a time. We're using only one worker here. The image size is the largest dimension of your image. So I'm going to actually add that here. Image size, largest, we'll do largest image dimension. So our images are 512 by 288. If you have rectangular images where the number of pixels in X and Y are not the same, you need to set this parameter equal to true. Otherwise, YOLO is going to struggle. So let's run it. Took a second to initialize, but it ran in 2 seconds. It should, in general, run quite a bit faster. And so now results was what we're trying to look at. So the first thing that I'll say is this results is actually a list of results of length batch size. Since we're just feeding in a single image at a time, there's going to be only one element in this list. So that's why I'm printing result 0. And here it is. It's an Ultralytics engine results object, and it has a bunch of attributes. So this is just to give you a very cursory walkthrough. So Ultralytics YOLO models support object detection. They support key point detection, which I mentioned on that one slide. And they also support segmentation. So if we had done segmentation, you'd be interested in the output of this masks attribute. We're just doing bounding box detection. So we're interested in this boxes attribute. The other attributes that are in this results object are primarily metadata. So this is just the PNG array of the input image, and then various other things here. So we want to, again, just to be extra clear, we want to look at this boxes object. So here's the result 0 dot boxes. That's how we open up the boxes attribute. And there's several more sub attributes of the boxes attribute. What we want here is data. So what these give you is this gives you the event classes that were detected in your event, as well as the confidence scores. But the reason why I'm taking data is data actually includes all of that. So let's go to this next cell where we look at .boxes.data. And this is, again, the output for our first image. And what is shown here, so the first thing that I want to write is, remember, image is 512 by 288 pixels. So each row represents a bounding box. So this is the coordinates of the bounding box. So x min, x max, y min, and y max. These are in pixels, and the way that YOLO does its inference, it does it at sub-pixel level precision. That's why these aren't integers. Then it gives a confidence score from 0 to 1. So 1 means perfect confidence, 0 means 0 confidence. Confidence score of the classification of the object. So here, the classification score is on the right. So this tells you that at these coordinates, we found an event that is classified as class 1, which class 1 is nuclear recoil. So let me write something here as well. Class 1 equals NR, class 0 equals ER. And yeah, that's what's shown here. So then the next step that we can do is we can visualize this. So this next function down here, it evaluates YOLO on the image and it plots it. So what we do is we have an image viewer that we've already defined earlier. So we first view the image. Then we're going to open up the actual raw PNG for that image. and then we're going to plug that into YOLO. So we run our YOLO model, we predict on it, we extract the boxes. One other thing is you'll notice this, if you have experience running PyTorch, because the back end of Ultralytics is PyTorch, it shows that this is a CUDA tensor. So it's on your GPU. Oftentimes when you do operations for this, you're going to want to mount it onto your CPU and also convert it into a NumPy array. So that's what's done here for our boxes. And then we just loop through the rows of these boxes. So in this event, there's 4 tracks, and we draw our bounding boxes. We plot them. So here is our first event right here. So truth group. And again, these are not the truth bounding boxes. This is what YOLO drew on here. Let's try another one. Here you can see on this track, which nuclear recoils, you see multiple scattering happen a lot. So that's what creates all of these extra prongs. But YOLO still said that there's a little electron recoil that's buried in there. So the white boxes are electron recoils. The red boxes are nuclear recoils. This should run pretty much instantaneously if you're on a GPU. But okay, so this is all fine and good. In a few minutes, we're going to see how this compares to truth. So we'll get to see how well YOLO actually does. But it looks, I'm just picking random numbers here. Okay, that one just had 1 track. Want to see if we can find another Migdal here. Eventually there'll be one. Yeah, here's one right here. It looks like it does a pretty good job being able to detect that electron recoil that is attached to the nuclear recoil. Okay, so this is an aside that is both important for today's module and just in general. So YOLO V8 and most of the Ultralytics YOLO modules, by default, they accept 3 channel images. So this means RGB color images. This actually isn't ideal for an analysis like this. So in a particle physics analysis, what we're measuring are 1-channel intensity maps. So the color scale that we have on here is really just for visualization purposes to visualize the intensity. So ideally, you want to be training and evaluating YOLO, in our case, on the 1-channel intensity maps. So Ultralytics has some YAML configuration files that basically have the neural network architecture of the model that you're using baked in. And you have to edit these files to be able to change your 3-channel image to a 1-channel image. The problem is doing this, it requires a little bit of sleuthing in order to find everything. And rather than making you guys do this today, because it is what you ultimately have to do, is you open up this YAML configuration file. It has these parameters here. Your backbone neural network, the input to that, so this is the first stage of the convolutional neural network of YOLO, you need to change this value of 3 to 1. That's how you do it. If you want to change the number of input channels. So rather than doing that, what we did here is the PNG images that I gave you are 3-channel. So just so to make this simpler, so we don't have to worry about modifying these fields. This is something to keep in mind, though, if you ever want to create a pipeline like this in your own research. So the color in these 3-channel images is not physically meaningful. That's something that's important. And it also could bias performance. And it could bias it both favorably or unfavorably. It's really hard to know. And so the way that we create these 3-channel PNG images is we set our color scale to a fixed dynamic range on the logarithmic intensity scale images. We're using the logarithmic scale images so you can see the electron recoils better. If you were doing this for your own application, you might want to, instead of using a fixed dynamic range, you might want to normalize your images based on say the pixel of highest intensity of your event. So there's a bunch of trade-offs in the way that you do your image pre-processing before training and evaluating YOLO. That's the point that I'm trying to make here. Um, and another point, if there's any astronomers in the audience, there's some applications where you might want greater than 3-channel images. If you're doing, I don't know, some sort of object detection pipeline with galaxies, and you're using survey data that has, I don't know, 5 or 6 bands where each band has physically meaningful information, you could actually change the input number of channels to the number of channels you need for your application. So other things to keep in mind there if you want to kind of make the most of your data. Okay, so thank you for listening to all of that. Now let's actually run our pipeline. So what I'm going to do is essentially we take that single image pipeline that we slowly built up here, and we then, so this is just a helper function here to compute the length of contents within YOLO's bounding boxes. We then make an inference pipeline. So this is already written here, but when you break down the code, it's actually pretty simple. So what it does is it looks for each event in your group data frame. So here, I is frame number, and it just runs YOLO on each of those frames. And then it extracts some information of interest from the bounding boxes. So, and then it writes that information into a pandas data frame. So that's all it does. So if you run this for a single event, it will give you, in fact, let's just do that right now. So we'll just set, I don't know, I equals 12, and we'll run this, and it gives you a data frame that shows that YOLO found 3 tracks in this image. All of them were nuclear recoils because prediction is 1. And it gives you information that's similar to our truth data frame. So it gives you the column, row, intensity, all of that jazz. This C is the pixel charge. Okay, so to run over our entire data set, we just loop through all of our data. So we concatenate the output of this over all of the events in our image frame index data frame. So if you're running on a GPU, it's actually running slower than I would like it to run because it's saying it's going to take 10 minutes to finish. So this is the stage where this output I saved, so we don't have to wait for this to run. So you can run this on your own time, but I would, for now, what I'm going to do is I'm going to interrupt this execution. And because we need to, yeah, we're at 3:30 right now, so I want to continue to the next cell. So now let's look at YOLO's output. If we had ran that previous cell, when I was doing this on my own, it was taking 90 seconds to run. So I'm not sure, maybe there's too much traffic on Google servers right now. But if we were running this and we had already generated it, we would just press out there. If you uncomment these last 2 lines and you comment out this one that says out, we can view the contents of this output. So this is the pre-saved version of it. And so it's like the data frame that I just showed on the single event, but now it shows all of the tracks that YOLO found. And there's 5,336 tracks that YOLO found when it ran through all of our images. So let's print this out, the number of tracks that YOLO found. You see that YOLO found 5,336 tracks, but the number of true tracks in our data frame is 4,700. So you might be wondering, is YOLO just really bad? Is it coming up with a bunch of false positives? And in this case, the answer is actually no. The reason why is YOLO was trained, like I mentioned in the slides, to only identify electron recoils and nuclear recoils. So in our truth data frame, we were treating Migdals as 1 track. In this YOLO output data frame, Migdals are treated as 2 tracks. They're an electron recoil and a nuclear recoil. So to double check, this next cell, what it does is it just loops through a truth data frame, And it counts whenever there's a Migdal that's found, it counts both the electron recoil and the nuclear recoil. So we can find the number of unique tracks. And when you do that, what you end up finding is in your truth data frame, there's actually 5,395 data tracks. And then in our YOLO output, we found 5,336. So we found, you know, we didn't find all of the tracks, but we got close. And a couple things to note. The looking at the difference between the number of truth electron recoils and the number of electron recoils YOLO found, YOLO missed about 60 of these. This might make sense because some of those electron recoils are very buried within the nuclear recoil for a Migdal event. So that might be the origin of some of these missing electron recoils. For the nuclear recoils, YOLO found one more than what is actually in truth. If we ignore that extra one, we don't know if they're one-to-one matches. That's something that we're going to check later on. But this is just kind of initial diagnostics on what we're finding. So now I think here I just have some events to plot. So this is now what we're going to do is we're going to plot YOLO's output on top of truth. So when you run this plot output cell, what this gives you is YOLO's predicted bounding boxes, which is kind of hard to see here. But if you look really closely, there's a narrow solid box and a boulder dashed box. The dashed box is YOLO's prediction. The solid box is truth. And so you can see in this frame, YOLO predicted the same number of bounding boxes as your truth data, and it did a remarkably good job. They overlap really nicely. Here's another one with nuclear recoils. They overlap nicely. We'll look at some more examples actually right here, I think. Oh, no. We'll look at some more examples later on. Okay, so the next stage of our analysis, so just giving you a sense on what we're going to do is, let's go back to the frame that had Migdals. So what we're ultimately going to try and do is we're going to come up with some criteria for what constitutes a Migdal. And you can see, for instance, the fact that these bounding boxes overlap, that's a good criteria for this being a Migdal event if YOLO finds an overlapping nuclear recoil and electron recoil bounding box. And then we're going to compare those with truth. But before we do that, let's just look at the intensity distributions of what YOLO outputted. So our YOLO pipeline, what it does is it computes the intensity and length of all of the pixels within a bounding box that it finds. And so when we look at the intensity for nuclear recoils, here's the distribution that we get. So we have in blue our predicted intensity distribution. So that's the contents of the bounding box that YOLO found. Orange is our truth intensity. These histograms agree very nicely. So that's good to see. But one thing that you'll notice is there's one nuclear recoil down here that YOLO found that doesn't seem to be there. In fact, it's below the threshold that we set earlier. Someone guessed the same threshold that I think I used here, 500,000 for intensity. This track fell below this threshold. So keep that in mind. Conversely, we can look at the electron recoil intensities. And when we do that, our predictions in blue, our truth is in orange. And when you look at this, you can see that in real data, there's this tail. Or not real data, in YOLO's output, there's this tail. And in fact, some of these electron recoils that YOLO predicts have intensities that are above our nuclear recoil threshold. So what's going on here? This is something that is a nice intuition builder, but I think in the interest of time, I'm just going to tell you what's going on here. So the main question is this something that we should expect? And this is why it's nice to actually look at your data. So what we can do is we can find the index of an image where our YOLO output had an electron recoil with an intensity that's too high. That's to the right of this black line. That's what this is doing. And then this is plotting the output of that. And what you'll notice is you see, for instance, this electron recoil right here that YOLO found. It's within that dashed bounding box. A bunch of the nuclear recoil leaked into it because they are overlapping tracks. And so what the takeaway here is even though we have electron recoil intensities that look too high, these are likely the result of being Migdal effect events where within the bounding box, we unfortunately also got some of the nuclear recoil's intensity. So we should be keeping these events. That's the point to make here. Conversely, if we look at this low energy nuclear recoil, so we plot the event where the prediction is, let's see, nuclear recoil. Did I get this backward? Maybe prediction 0 is nuclear recoil and the intensity. Oh no, sorry, this is the one that we want. Prediction equals 1 is nuclear recoil and the intensity is too low. This is the event that we see. So remember your truth bounding box is the solid and the dashed is your predicted bounding box. So YOLO predicted that this was a Migdal. In actuality, this is just a single electron recoil. So what I think happened is since we're looking at 2D projections, if tracks are kind of facing into the page, they can deposit a lot of intensity into the 2D plane, and that can create tracks that become false positives like this. But needless to say, there's nothing, this is just an event that YOLO didn't do well on. And I guess the bigger point is because your nuclear recoil intensity is so much higher than your electron recoil intensity, we should be applying our intensity cuts that we defined earlier to nuclear recoils. So if we do that, we remove this event. And so doing that, we make this new data frame called RED, which stands for reduced. And it just is your output data frame with where you're only keeping all electrons or nuclear recoils that have your intensity above threshold. That's what this is saying. Okay, so let's move ahead now and see how we can quantify our Migdal detection performance. So the metric that we use to quantify YOLO's predicted bounding boxes with truth is something that's called intersection over union. So I'm going to use this track to illustrate intersection over union. So what this IOU metric is it is the area of, so given two bounding boxes, so in this case, the ER bounding box and the NR bounding box, IOU is the ratio of the area of the intersection of these two bounding boxes. So that's the region I'm drawing with my mouse cursor here, divided by their union. And in that denominator, you subtract off the intersection. So divided by their union portion that is not the intersection. And this is a good metric to quantify how well your bounding boxes overlap. If your bounding boxes don't overlap at all, you have an IOU score of 0 because there's no intersection. If they overlap perfectly, you have an IOU of 1. So those are your limits. With the electron recoil and nuclear recoil predictions that we make here in Migdals, there should be an IOU greater than 0. So that's what we're going to be using today as our way to select for Migdal events. What we're going to do is in every single frame that we measure, in every single camera frame, we're going to scan through all of the tracks and pick electron recoils and nuclear recoils that overlap. There could be instances where you have more than one electron recoil overlapping with a nuclear recoil. So we're going to identify these in using computer science lingo in a greedy way. So it's a greedy search algorithm in that we're going to say an event is a Migdal uh, if it contains an overlapping electron recoil, nuclear recoil pair, and if it contains more than one, we pick the pair that has the highest IOU score. So that's what we're doing. And then we're going to say that's a Migdal. So uh, it's not so difficult in principle to code that out, but here's the actual code for it. So we're going to just run this long cell, and it does that for us. This is just to give you the intuition there. Um, and then the final step is, so once we've identified Migdals like this, actually, let's go back to one of these images, like right here. Once we've identified that this is a Migdal, because you can clearly see that these bounding boxes, the white electron recoil and the red nuclear recoil overlap, we then say, okay, is this a true positive or a false positive? We define it to be a true positive if both the electron recoil that is found by YOLO and the nuclear recoil that is found by YOLO, if it intersects or if it has an IOU greater than 0, so if it overlaps with its truth counterpart. So we require a predicted red bounding box to have an IOU greater than 0 with truth red bounding box, and same thing for the white bounding box. If that's the case for both, then we call this a true positive Migdal detection. So once you get down to the second long cell, we run this, and the output of this is going to be this data frame that's called merge scored. So we'll look at this. This has our predictions relabeled as what they are, ER and R. For single tracks, we use that same analogous IOU method to determine if it's matched correctly with truth. We have a Migdal that we found down here. And let's see, my notebook's freezing on me. It's not letting me scroll through. Let's try this again. Here we go. There is this is match quantity. If the Migdal that we found, so let's see this row right here. The Migdal that we found, if both the electron recoil and nuclear recoil that YOLO identified overlap with truth, then we say this is a match. That's a true positive. So with that, you can now compute purity and efficiency. And so the efficiency is going to be the length of your true positives that YOLO identified divided by your total number of Migdals in your sample. And then your purity is going to be the fraction of events after your cut that are true Migdals. And what we end up finding is a purity of about 98%, an efficiency of 87%. So we'll plot this, and you'll see that using YOLO and using this IOU metric to define a Migdal event, we're definitely closer to the optimal region of an efficiency of 1 and a purity of 1. Now, one thing to note here is this looks good in terms of the product of efficiency and purity is much higher than the product of efficiency and purity for any of our traditional baseline analyses. But this actually isn't going to be sufficient for us. And the reason why is when you're thinking about a rare event search, if we need a purity that corresponds to 1 in 100,000 nuclear recoil events, we really want to be seeing a purity that's higher than this. So now at this stage, you need to consider, okay, what else can we do to our YOLO output to get that purity up to 100%? And so there, at this stage, what I would do is I would dig into my data frame and figure out, okay, what are other columns that I can make cuts on that are going to, at the expense of efficiency, bring that purity up to 1. And so what you guys can try on your own, and I'll keep this to, I think, 10 minutes just in the interest of time, is when you look at these columns, things like match score, you can't use because match score actually has to do with, it uses truth information. And in a real search experiment, all you would have is YOLO's output. You wouldn't know the ground truth. So what these cells do, I'll show you an example, is it goes through the valid columns that you can make cuts on. So nuclear recoil length, electron recoil length, the intensities of those species, and the YOLO's classification score. So that probability of binary classification on whether it's a nuclear recoil or an electron recoil. You can input those columns into here and then compute your purity and efficiency. So here's just to show you an example. If we were to make, in addition to the Migdal selections that we've already made, so we predict Migdals, if you were to plot the true positives versus the false positives as a function of their nuclear recoil length, you could define a cut that removes all of the false positives. And if you remove all of the false positives, then you're at a purity of 1. So you can see here, if you were to define a nuclear recoil length cut that's greater than, I don't know, like 11 millimeters, you reject. So everything to the right of 11 millimeters here rejects all of our false positives and only keeps true positives. And so what that looks like when you loop through different values of cuts on nuclear recoil length, you can plot that here. It looks like something like this. So we do okay, but we don't do great using nuclear recoil length in addition to our YOLO selection. So what ends up happening is you make this cut. This is so close to 1, it's kind of hard to tell what's going on, but your purity gets a little bit better as your efficiency drops. And then eventually you reach the point where you get this. And what's plotted here is the first point where your Migdal selection purity is 1, and it shows what the efficiency is at that. So we get a purity of 1 at 34% efficiency using cuts on nuclear recoil length, which is better than the 18% that we got with our traditional analysis. So that's good to see. But try some of these other quantities to cut through and figure out which one performs best. And so I'll give folks maybe 5 minutes to work through that, and then we'll move on.
Maybe we can ask people to post how close they can get. That is what kind of.
Yeah, so yeah, that sounds good. So using these cuts, post the best efficiency that you can get that corresponds to a purity of 1. And I realize that this really is kind of just plug and play right now, but the key thing to pay attention to is looking at these histograms. You need to, if you were doing this on your own, you would define a cut on these histograms that optimizes or that basically keeps the most of events while having 100% of them being true positive. I'm gonna stop sharing for a second. So, okay.
Nice. I
So,
get
so
0.78. That's good.
yep. So someone is seeing 0.78, and they said that that is using ER probability. So let's do that. And yeah, this I hope that this builds up some intuition on how you would set this. I realize it's a lot of stuff that's plug and play that's thrown at you, but I hope that this gives some intuition on how this analysis could be done on your own. Yeah, so this is what ER probability looks like. Let's see. Okay, so just in the interest of time, I will say that is the right answer for this. And so I'm just going to run through this really quickly. So a lot of times when you are tuning your selection, so you can And in a real experiment, you want to tune your selections using simulation so you can understand how well your selection should do on real data. Um, and so with simulations, you do know the right answer. You know which are true positive and which are false positive. And you can see this ER probability is there's great separation here. You look at the vertical scale, which is a logarithmic scale. And so you see if you just only keep events where your ER confidence score is above around 1/2, you keep the vast majority of nuclear recoil, or sorry, of Migdal events that are true positives. And so that's exactly what you see in this plot here. So you reach 78% efficiency without any background contamination. So this really goes to show that using a method like this on the simulation set, it would allow you to basically get the same performance as energy versus length with running 4 times shorter, which that's great. If you have an experiment that needs to run for a year, which Migdal doesn't need to run for a year, but some experiments do. If you're using an experiment that needs to run for that needed to run for let's say 4 years using the traditional analysis, now it only needs to run for 1 year to get the same result. That's kind of how you can interpret these plots. The last thing to plot here, this isn't that important, but it just shows for the true positives that YOLO found. So this is the intensity versus length of the events that YOLO correctly labeled. And so the correctly labeled Migdals are shown in orange. And so you see it really can dig into this regime where energy versus length had no separation. Um, so that is the power of using object detection on this simulated data set. Let me just, so we have about 30 minutes left. Let me maybe spend 15 or so minutes just going through the rest of the slides, and then I'll take any questions after that. So um, the way that we do it on real data is essentially analogous. So I'm actually going to skip ahead here because I don't want to take the time there. And I'm going to skip this slide as well. So you guys saw how to quantify your performance on your simulation. How does the Migdal experiment actually do it for real data? And like I was mentioning a couple moments ago, you do need simulation to quantify your performance. But the way that we end up generating signal simulation to test our algorithms is using what I call a hybrid approach. So what we do is we take real nuclear recoils that we measure and we stitch simulated electron recoils. We stitch our simulated electron recoil vertex to the vertex of a real measured nuclear recoil. And that gives you the track that's shown on the left here. So we're taking real data nuclear recoils and adding simulated electron recoils to them to form a Migdal effect event. Why do we do this? The reason why is it turns out that we simulate low intensity electron recoils really well. We simulate nuclear recoils terribly. This gets back to why when I said that we tried the ResNet for Migdal classification and it didn't generalize well to real data. It turns out that's because our simulations are missing some key things when it comes to simulating nuclear recoils. These plots show this where for electron recoils, we have some topological variables where we're comparing data in orange and simulation in blue. They don't agree it perfectly, but they agree relatively well. For nuclear recoils, in a regime where they should agree, they don't. Data gives you much broader tracks with more pixels and systematically higher pixel intensities. This is something that we've actually now resolved, and it turned into a paper that is in prep right now because it turns out when you're measuring scintillation light, there's some optical effects in your detector that aren't simulated well, and so we've actually measured those effects now. So, but I digress. The point here is since simulated nuclear recoils don't agree with real data, when we try and generate signal simulation to quantify our performance, let's use real nuclear recoils. Um, you might be wondering, okay, if we're stitching events together like this, why are we simulating at all? Why aren't we just using real electron recoils and real nuclear recoils? And these are the reasons. Based off of the physics of how electron recoil tracks are generated, finding their vertices a priori is a really challenging thing to do. Um, that's a huge endeavor in and of itself. So simulation gives you that. The other thing is we risk double counting noise on real images if we tried to stitch a simulated electron or a real electron recoil to a real nuclear recoil. So the fact that our simulated electron recoils agree well with measurement, this is kind of the best simulation we can do. So in case some of that wasn't clear, we we use this hybrid simulation. Um, then in our experiment, what we are interested in our camera is identifying our efficiency of detecting the Migdal effect. And so I'm not including purity here because some of that purity also comes into dealing with more sophisticated background models. And so that's a more complicated study. But so what we want is just to make sure that our selections achieve adequate efficiencies for us. And so one of the extensions that you can try doing on your own time is looking at a detection efficiency versus electron recoil energy. Because if you remember, as I had said, the lower your electron recoil energy is, the shorter your track is. And so that means that those are harder to detect. And that's why we find these much lower efficiencies. But you can see as we get to higher and higher efficiencies, using YOLO, we do a pretty good job. Um, Now, in order to actually quantify the amount of migdals we expect to see given a certain amount of exposure to our neutron beam, you have to also look at the Migdal production cross section. So how likely is a Migdal event to happen at each energy? Um, and so that's kind of the next stage of the analysis. But what we're able to do just using this YOLO pipeline is we were able to take 20 million camera frames that we analyzed and apply similar selections to what you all applied in the module. And we reduced that sample of 20 million frames to about 800 frames. And here's real data. These are some examples of tracks that we found. Um, so at this stage, if you remember, I said we don't just have the camera readout, we also have that strip readout. This is the stage where you would need to correlate these events with your strip readout, especially because our camera exposure times are long. So if you align these with your charge readout, that charge readout has 2 nanosecond granularity compared to 8 milliseconds in the camera. Any events that align between both your camera and your strip readout, those are good Migdal effect candidates. Um, and so just to say something about this, there is a limitation with a 2D camera only analysis. And the limitation is in our experiment is the exposure time of the camera. So if you have a faster camera, you could do exactly what we did here, and that would be enough to say that these are likely the Migdal effect. But with a slow camera like ours, you can't do that with just the camera. Um, this event illustrates it here. So this is a real event that we measured. Here's your nuclear recoil, and here's your electron recoil. This is an unprocessed image, which is why the electron recoil looks exceptionally faint. But if you were to look at just the camera, this looks like a perfect Migdal effect event. But then when you look at our charge readout has 2 nanosecond timing resolution, and this shows the charge profile of this same electron recoil and this nuclear recoil. When you look at the timing from it, this electron recoil happened 5 milliseconds after this nuclear recoil, which means it was not the Migdal effect. It wasn't an electron that was simultaneously emitted. It was just because we collect so much data, every so often you'll find an electron recoil that spatially overlaps with a nuclear recoil. So the camera isn't enough on its own, but then you can combine it with the charge readout. So our charge readout, again, it measures XZ projections of events, but without going into much detail about it, we have these strips that measure charge versus time. And you can imagine rotating this kind of 90 degrees, and it gives you an image like this. So even though the strip readout isn't a physical camera like what we're using with our optical readout, you can still use YOLO on it, and you can identify something like this. So essentially, just let me first summarize our approach. So in Migdal, what we did was we developed a YOLO-based pipeline where we were able to train on real data because we identified that our rare event signal is a composite of two commonly observed species. So then we trained on real data, and YOLO is nice because it works with track overlap compared to naive clustering. Um, and then you can use the locations of the classified species to select for events that are consistent with our Migdal effect signal. And you can really do this with any kind of detector readout that can express its data as images. So you're not limited to an optical camera. So this is how this approach can be um, adapted to other experiments. In any cases where you have a composite rare event signal, you could develop a pipeline like this. So I'm going to come back to this in just a moment. So one application where this could be done without going into any detail. So I'll hopefully post these slides so you can look at this on your own time. But neutrinoless double beta decay is one kind of example where you can have there's certain experiments like Next and I think Panda X3 actually might no longer be funded, but Next is a gas TPC experiment that tries to visualize neutrinoless double beta decay events. And these are events where it is two events that can be commonly observed if you use radioactive calibration sources that share a vertex. And so you could use some sort of bounding box type analysis to identify those events. It's something that could even potentially be used on the front end as a trigger for barium tagging. And I apologize that this is in the weeds. I don't have time to motivate this properly. But so that's one example. There's other experiments that use optical TPCs to image exotic decays. So using this overlapping bounding box method can be a way to help you reconstruct decay vertices using image data. So those are two other examples where this can be used. What I want to talk about is just one additional extension for Migdal, since that's what we've been focusing on. And so it's all fine and good if you can identify the Migdal effect, but ultimately our goal is to validate that theoretical cross-section distribution. So that was this image that I showed at the very start of the slide where theory predicts Migdal production rates as a function of both nuclear and electron recoil energy. So we want to get enough data points ultimately to be able to validate this theory. And you can see, looking at the Migdal effect events that you saw in your module, this is pretty challenging because we need to reconstruct the nuclear recoil energy, which that's not so big of a deal because the electron recoil doesn't add much to that. But in order to map the electron recoil energy, which this cross section really strongly depends on, again, this is a logarithmic color scale, you need to be able to reconstruct the energy of an electron recoil that is buried within an orders of magnitude brighter nuclear recoil. So how do you do this? One way would be to build a better detector. So one of the things that I didn't talk about is the reason why our tracks are broad has to do with the way that electron drift works in time projection chambers. And so your tracks diffuse as they drift in your detector and it broadens them. You can have detectors that use different readouts, not optical readouts due to scintillation properties, where you can put in a dopant gas that makes negative ions drift instead of electrons to form your tracks. And those, if it's heavier negative ions that drift, like a CS2 minus ion, that is going to undergo less diffusion because it's much more massive than an electron. And so when you develop a detector like that, it takes an alpha track or a nuclear recoil that looks something like this. It makes your track much narrower. So you can imagine then that your overlap region is much smaller than what's shown here. But okay, so that's kind of the cop-out answer. You could build a better detector, but could we do this with our existing data? And we're finding that you actually can. And so this, I don't have time to do this full justice, but I'll say that our collaboration developed a segmentation regression framework. We call it OASIS, standing for Overlap Aware Segmentation of Images, where I told you about that hybrid simulation that we make where we stitch simulated electron recoils to measured electron recoils. What we did was we developed a segmentation regression pipeline where we use these hybrids as our training data. So we develop a pipeline where you start with your hybrid event where these two were stitched together, and you train a neural network to undo that hybrid into two images. The first channel being the intensity contributions of your electron recoil, and the second one being your intensity contributions of your nuclear recoil. What is kind of unique about our approach is the loss function that we use. And so for segmentation regression, what you're ultimately doing is you're training a neural network to, when you look at each of the channels that are output by your neural network, you want each individual pixel's absolute intensity difference between your prediction and the true version of both the electron recoil and nuclear recoil channel to be zero. That's what optimizes this function. And what we add in are these, this is the novel part, we add in these region-specific weights that basically in your training data, if a pixel has both electron recoil content and nuclear recoil content, we call that an overlap pixel, we weight those heavily in our training. So we weight it so that we try and optimize the pixels that are in our overlap region. What that ends up giving us is something that can do a really good job of, given an event like this, where we have our electron recoil and our much brighter nuclear recoil here, we can predict an electron recoil that looks like this. This is what it looks like within the region that's buried in the nuclear recoil. Here's the true answer. They look qualitatively similar. The direction that you can map to this event, if you fit a curve to it, ends up aligning really nicely. And we get energies that align nicely. Even with events where your electron recoil is really buried, we get something that does a pretty decent job. We validated that this model doesn't hallucinate, and that if you take a nuclear recoil only, as it should, it doesn't predict an electron recoil. And going back to that weighted part, what we did was we compared the track intensities that you get, so summing up the intensity of the pixels here, comparing it to truth. We computed that percent difference using a normal segmentation regression loss function. So one where all of the weights here are set to 1. That's naive segmentation regression, which is well established. And we get this curve. So 0 is perfect performance. It means that your intensity reconstruction matches real data. And then when we added our weights to our training, it significantly improved performance, particularly for these low energy electron recoils where you're dominated by overlap. So what this is telling us, just connecting back to the big picture, is that using a technique like this, we actually might be able to start mapping a cross section like this with our existing detector, which is something that we didn't originally think we could do in this generation of our experiment. And finally, this is the correlation curve between your predicted electron recoil energy and truth. So thank you very much for listening to this. I'll leave you with the current status of the Migdal experiment. So we are still collecting data, and a search result paper is currently in progress. We've actually been limited in the amount of data we've been able to collect. We've only collected about 170 hours of data over the last couple of years because our neutron generator was breaking. Fortunately, it's now repaired, so we're planning to take a much longer science run in 2026, and the hope is that we'll be finding many Migdal effect events. Um, so I'll leave you with a slide that just has some links to some papers and software to learn more. Um, so thank you all for your attention, and if there's any questions, I'll happily take them now.
Jeff, maybe we can say we'll try to post the paper on the same Google Drive so that people, or the slide, not the paper, the slides, so people
Yeah,
can access them afterwards,
yeah, that sounds good.
particularly for
I'll
the
actually,
references.
yeah, I think I have access to do that. So if I do, I'll just post them, post the slides.
And again, this recording will appear in hopefully a few days on the on Brown's physics department YouTube channel. So you'll be able to play back. And for those of you on, even for the people who weren't able to attend, you will have access to the Google Drive. So of course you can rerun the notebook on your own. So are there any last minute questions for Jeff? Oh, there's a question about the loss function, how the loss function can help decompose events that are overlapping.
Yeah. So um, basically, so that's a good question. So essentially, the majority of the loss function that we're using is meant to optimize segmentation regression. And so segmentation regression means predicting at the pixel level of granularity. So for each individual pixel, predicting its intensity. And so essentially, when you are running a training loop for your neural network, you're trying to minimize this loss function. And so what we have in terms of our terms here, really the numerator is all that matters, the denominator is normalization. What we're trying to do is we're summing over our two channels. So in our case, it's the electron recoil and nuclear recoil channel in our training data, because we're training it on these hybrid events. So we have exactly one nuclear recoil and exactly one electron recoil. Um, so we sum over the channels, and then we sum over all of the pixels in our region of interest. So all of the pixels inside YOLO's bounding box. And we take the absolute difference between your model's prediction and truth for each of the channels, and you sum those together. What these weights do is if you assign a large value for the region weight, like what we did here to get this orange curve, we assigned an overlap region weight of 6. What that means is if we just made W region 6 and everything else 1, it means that in optimizing our loss function, you are heavily weighting the region of pixel overlap to optimize your loss function compared to, the region where my mouse is right here where there isn't any overlap. Um, and so by
You're
tuning these
you're not
weights,
sharing screen, so people can't
oh
actually
my
see the
goodness, I'm
mouse.
so sorry. I thought that I was sharing my screen. Um, I'm sorry about that. Yeah, so let me go back to this. So the segmentation regression function, we can ignore the denominator because it's just normalization. What we're trying to do is we are summing over both of our channels, so the electron recoil and nuclear recoil channel, and we're taking the absolute difference of your predicted pixel intensity in both channels to truth. And so by applying this region weight where you select pixels that, and you can do this algorithmically by just treating this as a tensor of two images. If you find pixels that are non-zero in both the electron recoil and nuclear recoil channel in truth, you assign those as overlap pixels. And if you assign, say, a factor of 6 here, what that means is in your training, when your model is going through back propagation and optimizing your segmentation regression loss, um, you're saying that these pixels in the overlap region are 6 times more important than the pixels out here where they're not overlapping. And it turns out in our case, that really helps. It ends up giving you, you can see that the orange curve is significantly better than the blue curve where you weight everything the same. And so that's the idea of what happens is when you're developing a loss function like this and you're thinking about the application at hand, you do want to think about, okay, which regions do I want to weight? Um, if this framework, you don't have to just use it's extendable beyond Migdal. You could do this for any amount of overlapping objects. You would just have to define region weights for each class of object overlap that you end up having. So it becomes eventually, if you have too many objects that are overlapping, it might become combinatorially too difficult. But at least in our case for Migdal, where we only have two objects, it works pretty nicely.
So if there are no more questions, let's thank Jeff again.
All right.
This
Thank you
concludes.
all for attending. And thanks for setting this up to all of the media people and Jan.